In this video, we're going to discuss the solutions for the midterm exam on linear algebra during this fall semester 2019. Exam contains two parts. The first part contains short answer questions, and the second part contains the 7 problems on the following topics. Let's start with the first part. So we need to find the entry of the position 4 and 2 for this matrix. So in order to do this, we need to multiply the false row of this matrix to the second column of this matrix B as a scalar product, right? So we multiply 3, 3, minus 1, 2, 1, 2 to the column vector 0, minus 1, 3, 3, minus 2, minus 2. So if we multiply them, we're going to multiply them component-wise. So 3 to the 0, 3 to the minus 1, minus 1 to the 3, 2 to the 3, 1 to the minus 2, 2 to the minus 2. So we can cancel these terms, and what is left here is minus 6. So this is going to be minus 6. So we're given 3 vectors and we need to do the following operations. So in the first case, we need to multiply the B transpose to the A. This is just the scalar multiplication of these 2 vectors. We can just multiply them component-wise. It's going to be minus 1 to the 3, 3 to the 2, 4 to the 1. So what we obtain is here 7. So we need to find the norm of the C. So the norm of the C is obtained by taking the sum of the squares of its component, which is going to be 9 plus 1 plus 4, and take the square root from this, which is going to be square root of 14. And in order to find the unit vector in the same direction as the C, we need to divide each component of the C to its norm. In the question number 3, we need to find the inverse of the following matrix. I see that this is the elimination matrix. What it does is it multiplies the second row to the 2, and it does this to the third row. And the inverse of this operation would be if I multiply the second row to the minus 2 and add it to the third row. Basically subtract the minus 2, multiply to the row 2 from the third row. So that is why the inverse is going to be like this. So for the following matrices, we need to do the operation. So we first of all take the transpose of the B. It is obtained by writing down every row of this B as a columns. It's going to be 2, 1, 3, 1, 2, 4, 5, 3, 2. So in the second stage, we need to multiply the A to the B. So I see that I can multiply this 2 matrices as a combination of the rows of this matrix B, right? So I need to use this A as a coefficient matrix and this B as the vectors. So this is the permutation matrix, right? Where I have to interchange the first row with the second for this matrix B. So if you multiply the A to the B, the first row and the third row of the B are going to be changed. It's going to be 2, 1, it's going to be 5, 3, 2, 1, 2, 4, 2, 1, 3. So now if we multiply this AB to the C, right? So I can now combine the columns of this AB matrix using this coefficients. So this looks to me that again the permutation matrix where I have to interchange the first column was the third column. So it's going to be 2, 4, 3, 3, 2, 1, 5, 1, 2. So for the following matrix, we need to find the elimination matrix E2, 3. Basically, if I would like to eliminate this 1, I have to multiply the third row to the minus 1 over 2 and add this to the previous one, to the second one, right? So the third row should be multiplied to the minus 1 over 2 and should be added to the second, right? And I should not change the first row. Okay, all the other rows are going to be the same. So the elimination matrix like this. So basically, I kept the first row as it is, the last row as it is. So I'm going to change the second row, and I'm going to change this in a way when I multiply the third row to the minus 1 over 2 and add this to the second. So if A and B are the t-square matrices, we need to open the brackets. A plus B in the square is equal to the A plus B multiplied to the A plus B. Then we need to open up the brackets by just multiplying the every matrix from the first bracket to the every matrix from the second bracket. It's going to be A squared plus AB plus BA plus B squared. So please note that AB is not equal to the BA in general, so the matrix multiplication is not associative. Let's start solving the problems from the second part. So we're given a matrix, we're given a system of linear equations, so we need to solve this using the inverse of this matrix. So first of all, need to copy the coefficients of the system of linear equations. It's going to be 1. So in order to find the inverse of this matrix, we copy the coefficient matrix and identity matrix just after this, and bring this matrix to the reduced row echelon form, and we can see the inverse of this matrix at the end. So in order to bring this to the reduced row echelon form, which is the pivot from the first row, and eliminate all the entries below this, we basically multiply the first row to the minus 4 and add this to the second. So please note, in this case, I'm not going to change the entries on the first row. It's going to be 0 here, minus 2 multiplied to the minus 4 is 8, 8 plus minus 6 is 2, here minus 1, minus 4, 1, 0. So in order to eliminate this minus 2, I need to multiply the first row to the 2 and add this to the third one. And what we obtain here is 0. So minus 2 multiplied to the 2 is minus 4, plus 6 is 2. 1 multiplied to the 2 is 2, minus 4 is minus 2. Then it's going to be 2, 0, 1. So this is going to be the pivot. Now we need to go to the second row and choose the first non-zero element and eliminate all the entries below this. In order to do this, we multiply the second row to the minus 1 and we add this to the third one. So please note that in all the other rows are going to be unchanged. 0, 2, minus 1, minus 4, 1, 0. Now we multiply the second row to the minus 1 and add this to the last one. It's going to be 0, 0. Minus 1 multiplied to the minus 1, it's going to be plus 1. And if we add this, it's going to be minus 1 here. Minus 4 multiplied to the minus 1 is 4. Plus 2 is 6. Minus 1 and 1. So this is almost in the row echelon, in the reduced row echelon form. This matrix is already in the row echelon form. In order to bring this to the reduced row echelon form, we need to choose now the pivots starting the last row and eliminate the entries above them. Right? So the first thing what we are going to do is, it would be easier for us to work with the ones on the pivot positions, right? So we multiply the third row to the minus 1, and we multiply the second row to the 1 over 2. So in this case, we're going to obtain 1 minus 2, 1, 1, 0, 0, 0, 1, minus 1 over 2, minus 2, 1 over 2, 0, 0, 0, 1, minus 6, 1, and minus 1. So now in order to eliminate this minus 1 over 2, we multiply the third row to the 1 over 2 and add this to the second. And in order to eliminate this 1 on the first row, we multiply the third row to the minus 1 and add this to the first row. So let's do these operations. So the last row is not going to be changed. Now I'm going to change the second row. It's going to be 0 here. Minus 6 multiplied to the 1 over 2 is minus 3. If I add this to the 2, it's going to be minus 5. 1 multiplied to the 1 over 2 is 1 over 2 plus 1 over 2 is 1. and it's going to be minus 1 over t. If I multiply the third row to the minus 1 and add this to the first one, we are going to obtain 1 minus t, 1, oops, sorry, 0. So minus 6 plus 1 is, minus 6 multiplied to the minus 1 plus 1 is going to be 7, minus 1, and 1. So now we need to choose the pivot on the second row and eliminate all the entries about this. So we can do this by multiplying the second row to the t and adding this to the first one. So the last two rows are not going to be changed, so I can just copy the third row and the second. Now we have to multiply all the entries on the second row to the t and add this to the first one. It's going to be 1 here, 0, 0. So minus 5 multiplied to the t plus 7, it's going to be minus 3. 1 multiplied to the t minus 1, it's going to be 1. Minus 1 over t multiplied to the t, it's going to be minus 1 plus 1, it's going to be 0. So this is going to be the inverse of the matrix A. And now, in order to solve the system AX is equal to the 0, we can just multiply the inverse of the matrix A to the B vector. So it's going to be minus 3, 1, 0, minus 5, 1, minus 1 over t, minus 6, 1, and minus 1. So we just multiply to the 1, 0, 1, and it's going to give us the vector x. So when we multiply a matrix to some vector, we can look to this as a combination of the columns, where the columns are multiplied to the entries of this vector, right? So this vector means that multiply the first column of this matrix to the 1, second column to the 0, and the third column to the 1. Basically, we just need to add the first column with the third one. So it's going to be a minus 3, minus 5.5, and minus 7. That's the answer. Let's discuss the solutions for the second problem. In the second problem, we're given a system of linear equations. Ax is equal to the b. We need to find the complete solutions for this. So in order to do this, we first of all need to write down the augmented matrix, where we put the a coefficient matrix and a b vector all together to the same matrix and bring this matrix to the reduced row echelon form. And we can do this by multiplying, by choosing the pivot on the first row and eliminating all the entries below this. We multiply the first row to the minus t and add this to the second. And later we multiply the first row to the minus 4 and add this to the third row. In the next step, we choose the entry on the second row. It's going to be 1, and we're going to eliminate all the entries below this. And we can do this by multiplying the second row to the minus 1 and adding this to the third row. We're going to obtain 1 t minus 1, 0, 1, 0, 2, 0, 0, 0, 0. So we can see from here that the first column and the second column are the pivot columns because they have the pivots, right? And the last column is going to be the free column since it doesn't have the pivot. So that is why x3 is going to be the free variable. So the free variable is x3, and in order to find a particular solution, we just need to solve the system of linear equations. So let me write down the system of linear equations. It's going to be x1 plus txt minus tx3 is equal to minus 1. xt is equal to the t. It's the rx is equal to the d system. So in order to find a particular solution, we set the free variable x3 to be equal to the 0 and solve this. So if we set this to be equal to the 0, we're going to obtain the system x1 plus txt is equal to the 1, xt is equal to the t. So if we substitute x2 to be equal to the 2 to the first equation, we obtain x1 plus 4 is equal to the 1. xt is equal to the 2. From here we obtain x1 is equal to the minus 3, and the particular solution is going to be minus 3, 2, and 0. So now we need to find a special solution. So since we have only one free variable, we're going to have only one special solution. And in order to find a special solution, we set x3 to be equal to the 1, and we solve our x is equal to the 0. So we basically solve the system where the right hand sides will be just simply 0. x1 plus t, x3 minus t, x2 minus t, x3 is equal to the 0. xt is equal to 0. If we substitute x3 to be equal to 1 and x2 to be equal to the 0 for the first equation, we obtain that x1 is equal to the 2, x2 is equal to the 0 from the second equation, and x3 is equal to the 1 as we set up in the beginning. So it's going to be 2, 0, 1. It's a spatial solution, and the complete solution for the system, it's going to be at x particular, which was minus 3, 2, and 0, plus the span of the spatial solutions, which is 2, 0, 1, multiplied to some constant t for all values of this t from the real numbers. Problem number 3, we need to find the LDU decomposition of the following matrix. So please note that here there is a typo. So here the original matrix have 6 here and 5 when I copied this, and 5 here and 6 when I copied this. So in both of the cases, even if you corrected this to the 6 and 5 or 5 and 6, you will be able to find the LU decomposition of these matrices. So we can continue with this matrix. So in order to find the LU decomposition of this matrix, we need to eliminate the entries below the diagonal of this matrix A. We need to bring this matrix to the upper triangle matrix. So we need to eliminate this t first of all. So in order to do this, we multiply the first row to the minus 1 and add this to the second, right? It is how we're going to change the second row. So now we multiply this 1, 0, 0, 0, 0, 1. If we do this, we're going to obtain 2, 4, 4, 0, 1, 1, 2, 4, 6. So now we need to multiply this matrix. So we need to eliminate this t in this matrix. In order to do this, we multiply the first row to the minus 1 and add this to the last one. And we're now going to change the first and second rows. So if we multiply this to the 2, 4, 4, 0, 1, 1, 2, 4, 6, what we're going to obtain is 2, 4, 4, 0, 1, 1, 0, 0, and 2. Okay, so this is going to be the U matrix. So in order to obtain the L matrix, we need to multiply the inverse of the E1 to the inverse of the E2. So the inverse of the E1 is going to be simply 1, 0, 0, 1, 1, 0, 0, 0, 1, and the inverse of the E2 is going to be 0, 1, 0, 0, 0, 1, 0, 1, 0, 1. So we can multiply the two matrices as a combination of the rows of the second matrix or the combination of the columns of the first matrix. So we can do this, the combination of the rows of the second matrix. It means that I need to copy the first row and the last row as they are. It's going to be 1, 0, 0, 1, 0, 1, and the second row is going to be changed. Second row of this matrix is going to be changed when I multiply the first row and the second row to the 1 and add them. It's going to be 1, 1, 0. Basically, I need to add these two rows. So this is going to be the L matrix. So now we need to copy the L matrix. It's going to be 1, 0, 0, 1, 1, 0, 1, 0, 1. And please note that here I need to bring the LDU decomposition, right? Not simply LU decomposition. So LDU decomposition means that the diagonals of this matrix U, I should have 1s. So we can simply copy this first of all. It's going to be 2, 4, 4, 0, 1, 1, 0, 0, 2. So if I just don't want to change the L multiplied to U gives me the A, right? So which matrix I need to put here so that this multiplication do not change? It's going to be just simply identity matrix. So now what I want is I would like to make this T to be equal to the 1. So if I would like to make this to be equal to the 1, I need to put here simply 2. Right, so please note that when you multiply the diagonal matrix, some matrix here, it's all the rows. So the third row of this matrix, it's going to be simply multiplied to the 2. So I don't change the second row, and on the third row, in order to make this 2 to be equal to the 1, I need to divide all the entries here to be 2 to the 2. It's going to be 1, 2, 2. Since I divided everything, I have to multiply this everything to the t as well. So this is going to be diagonal matrix. If I multiply this first row to the 2 and the last row to the 2, we're going to obtain exactly the U. In the following problem, we need to find the identify independent vectors. So basically, we can just put them to the matrix and find the pivot columns. They are going to give me the independent columns. So if I put everything to the matrix, so I need to eliminate all the entries below this. So basically, I multiply the first row to the 1 and add this to the second. We're going to obtain 1, 1, 1, 0, 0, 0, 0. So first row is multiplied to the 1 and added to the second. 1, 0, 1, 1, 1, 1, 0. And I just copied the last two rows. It's going to be 0, minus 1, 0, minus 1, 0, 1, 0, 0, minus 1, 0, minus 1, minus 1. Now we need to go to the second row, choose the pivot, and eliminate all the entries below this. We can do this by multiplying the second row to the minus 1 and add this to the third row. So we are not going to change the first row. We're not going to change the second row. We multiplied all the entries on the second row to the minus 1 and add this to the so not minus 1, so simply 1, sorry. Simply 1 and add this to the third row. It's going to be 0, 0, 1, 0, 1, 1. And I copy the last row as it is. Now we need to go to the third row. This is going to be the pivot. We need to eliminate all the entries below this. And we can do this by multiplying the third row to the 1 and adding this to the last row. So in this case, I need to copy the first row, second row, third row, and we need to multiply all the entries on the third row to the 1 and add this to the last one. It's going to be 0, 0, 0, 0, 0, 0. So now we need to identify the pivot columns. It's going to be, so this column has the pivot here, here, and here. So these three columns have the pivots, and the last three columns do not have the pivot. So that is why the first three vectors are going to be independent vectors. So the largest possible number of the independent vectors among the 6 is going to be equal to the 3. So the question number 5 is a little bit theoretical. It's about define the number of solutions for the system of linear equations Ax is equal to the b. So let's start from the first one. So we need to figure out a matrix Ax is equal to the b so that the system has either 0, no solution, either exactly 1 solution depending on b. So in this case, I can choose the vectors like this. So let me choose this 1, 2, 3, for example, or 1, 0, 1. So I need to multiply this to the x1 and x2 because there are 2 columns, right? And so since this matrix is 3 by 2, this vector is 2 by 1, the answer should be again 3 by 1 vector. So b1, b2, b3. So basically what I'm asking you is, so combine these 2 columns, right? So you got the 1 vector, this is the first column of the A, and the second vector, this is going to be the second vector of this matrix A. So what combination of these 2 vectors is going to give you the third vector B? This is the question. So so all possible linear combinations of these 2 vectors is going to give you a plane in R3, right? So if this vector B is on this plane, then you can find this vector B and the solution is going to be unique. You can find only one vector, one combination which is going to give you this vector. But if this vector B is outside this plane in R3, because there are many other planes in R3, then the system has no solution. So this is an example of the case where the system Ax is equal to the B have either 0 solution if the B is not in the plane, either 1 solution if the B is in the plane in R3. So the system of linear equations have infinitely many solutions regardless of B. So in this case, I can choose the column. It's like 1, 0, 2, 0, 1, and 1, for example, like this. So in this case, I need to multiply this as x1, x2, and x3, and this should be equal to b1 and b2. So in this case, the system has infinitely many solutions no matter what is the B, regardless of B. So basically what I'm saying you, hey, so I've got the two vectors here and the third vector like this, and this is going to give you all possible. So it doesn't matter what is the B, it's going to have the infinitely many solutions always. So 0 or infinitely many solutions depending on B, right? So basically I can write this down as 1, 0, 2, 0, let's say, multiplied to x1 and x2 is equal to b1 and b2. So this system has either infinitely many solutions, either zero solution, depending on B, because so the first two columns of the matrix A are just the parallel, are lying along the line, right? So if this B is again given on this line, then you can obtain this green vector by combining these two red vectors with infinitely many combinations. But if this vector B is outside this line, then you cannot obtain this blue vector as a combination of these two red vectors. Never, right? So if the B is outside this line, then the system has zero solution. If the vector B is on this line, then the system has infinitely many solutions. So this is this example of the A when the system has either zero, either infinitely many solutions. And the system has exactly one solution regardless the B, so it's going to be just the invertible matrix 1, 2, 3, 4. So this matrix is invertible, so that is why any system of linear equations Ax is equal to B is always going to have the unique solution, and this solution can be obtained by multiplying the inverse of the A to the B. So we need to find the inverse of this A matrix. So it's luckily we're given the pattern of this A inverse, right? So please note that if I multiply the A to its inverse, I need to obtain the identity matrix, basically 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. So I can obtain this 1 by multiplying the first row of the A to the first column of the A inverse, right? So let's multiply this. 4 minus 1 minus 1 minus 1 multiplied to A, B, B, A, B, sorry, should be equal to 1, right? Because if I multiply the first row to the first column, I need to obtain 1 since they are inverses, right? So if I multiply the first row to the second column, I need to obtain this entry, and it should be equal to the 0. So basically 4 minus 1 minus 1 minus 1 multiplied to the second column, which is B, A, B, B, it should be equal to 0. Basically, I've got a two-system of linear equations with the two unknowns, and I need to find A and B. So in this case, it's going to be 4 minus B minus B minus B is equal to the 1. For A, for B minus A minus B minus B is equal to the 0. So if we simplify this, it's going to be 4A minus 3B is equal to the 1. 2B minus A is equal to the 0. So from here I can obtain that A is equal to the 2B, and I can substitute this as the first equation. It's going to be 8B minus 3B is equal to the 1. So it means that the B is equal to the 1 over 5. And if I substitute this to the A is going to be equal to the 2 over 5. So the inverse of this matrix A, it's obtained when I substitute the A to be equal to the 2 over 5 and B to be equal to the 1 over 5. So basically I need to substitute all the appearances of the A to the 2 over 5 and all the appearances of the B to the 1 over 5, and it's going to be the inverse. Problem number 7, it's we need to show whether this is the vector space or give a specific example to contrary. So basically, I see that this is the equation of the plane, right? So we can see this in this way. So let me write down the system. Ax minus 1 is equal to xt plus t x3 for all possible values of the x1 and x2. So basically, I need to find all possible points with the components x1, x2, and x3, which are satisfying this equation. There are infinitely many points. So where xt and x3 are the free to choose, so I can set up to the parameters t1 and t2, and I can find x1 from the first equation. So x1 from the first equation is going to be equal to t1 divided to the 5 plus t2 divided to the 5 plus 1 over 5. So xt is equal to the t1, x3 is equal to the t2. So if I write down all possible points which satisfy this equation with the components x1, x2, and x3, we can obtain this in this way. So 1 over 5 plus t1 over 5 plus t2 over 5, t1, t2. If I split this to the t1 and t2, what we're going to obtain is 1 over 5, 0, 0, plus 1 over 5, 1 and 0 multiplied to the t1, plus 2 over 5, 0 and 1 multiplied to the t2 for all values of the t1 and t2. So please note that this is the equation of the plane, where we could write down this as the x is equal to x0 plus 1 vector multiplied to the t1 plus another vector multiplied to the t2. But unfortunately, this plane is not passing through the origin. Right? So if you substitute t1 to be equal to the 0 and t2 to be equal to the 0, what you're going to obtain is 1 over 5, 0 and 0. This is not passing through the origin. So this plane is not passing through the origin, so that is why this is not a vector space, right? So if you remember in the lectures, we discussed this case. So if the plane is not passing through the origin, for example, in this case like this, right, where this plane is going to be 1 over 5. So if this is x here, it's going to be 1 over 5 here. Then if you choose the t vectors, any t vectors, the linear combination should be also here. But unfortunately, if you multiply this t vector to the 0, you're going to have this vector at the origin, which is outside this plane, so that is why this is not a vector subspace. So any plane which is not passing through the origin is not a vector space.